Welcome to this video on inductors part 3. We're going to be taking a look at a few different scenarios here of inductors placed in an LR circuit and see what happens when we make some variations. So we have an EMF power supply here. We have a inductor and a variable resistor, and it's important that we have something that can vary because we know that inductors only respond to changes. They don't respond just to the mere current running through. They respond to changes in the current. Now I'm going to be using conventional current, so we know that the current is going to be flowing from the positive to the negative, so it's going to be going clockwise here through this circuit. And so what we're going to do is first is we'll go ahead and drop the resistance. Now doing that is going to cause the current to increase. So an increase in the current here is going to cause the inductor to respond. So if we remember, as soon as the current starts to increase, the field that is produced around the wire will increase and the flux through the inductor will increase, and so the induced flux is going to push back in the opposite direction. So in essence, what we're going to have here is a back EMF. Now when I say back EMF, we see here that this inductor is essentially going to form a situation where we have something that looks like this. I like drawing it this way because you can see here, if you remember doing a Kirchhoff rule, we would say EMF here, we'd go up, so have a positive voltage increase, and then here we'd have a voltage decrease. And that's what we want to see. We want to see that it's actually pushing against the current. Now it's not going to cause the current to decrease, but it will kind of slow it down, and so the rate of increase will be decreasing until it reaches a steady state again. And then the inductor behaves as a wire after that point. So let's take a look now. What if we increase the resistance? What would happen? So here I have the same circuit again, and what we're going to do now is take the resistance and increase it. And by increasing the resistance, what's going to happen is the current is going to start to drop. So again, the direction of the current is really important. We know that the current is flowing clockwise according to the conventional current directions from positive to negative. But now let's analyze what's happening here at the inductor. So the current starts to drop, so the magnetic field will start to fall, the flux will start to decrease, and in a response to maintain the equilibrium, the inductor will try to prevent the drop. So now it's almost going to be assisting the direction of the current. And so what we should have here would be essentially some sort of an EMF generated in this direction, where we have it in the opposite direction that it was here. And what's more important, I think, than that even is looking at the fact that they're in the same direction, the same orientation. So it's going to help push the current forward. Here they formed in the opposite orientation. So just with like with our studies of Lenz's law and Faraday's law, when we were first learning about that in inducing an EMF in a separate coil, we want to think of the fact that we don't want change to occur. So there is a natural response in the opposition of change. So as soon as something starts to increase, we want to prevent the increase. As soon as something starts to decrease, we want to prevent the decrease. Well, you prevent a decrease by supporting, so you go in the same direction. You prevent a decrease, or prevent a increase by opposing the direction. So it's not always just an opposition, because here obviously it's not an opposition. It's always an opposition to change. So the key term here is always change. If there's no change occurring, then there will be no response of the inductor. Now in the next video, what we're going to do is come up with the equation for the current function, and we will take a look at that, and we can also take a look at how the EMF across the or the voltage across the inductor changes as a function of time.